Welcome to lesson 4.3. In this video, we're going to focus on our critical numbers. In this case, the ones we're focusing on are our maximums and our minimums. These are also known as extrema. Now, our maximums are any place along a function that is, our y value is higher than the rest of the function, kind of our peaks, if you will. Our minimums are the places where it's lower than anywhere else on the graph or on the function. These would be like our valleys. Now, in this case, the function we've been given has got a domain restriction on it. It goes from -20 to 20, which means that we can consider the endpoints as part of these maximums and minimums. If the endpoints went to infinity or negative infinity, then we would not be able to, because there is not a specific y value to it. So in this case here, we have this endpoint right here at x equals 20 that's higher or has a higher y value than all of the other maximums. So this would be known as our absolute maximum. The others would also be maximum points, but these would be known as relative or local maxes. Okay, on the minimum side, it's the same thing. In this case, our endpoint also has our absolute minimum value, which is the lowest y value of all of them. And then there's two relative minimums found, one in the -5 area and one in the positive 15 area. And these are both relative minimums. They're the minimum point for that area. Now, one of the things I hope that you noticed is that these are areas where our tangent lines are going to be horizontal. They're where the graph changes direction. And that's kind of cool, because what that means is that when we look at our derivative, and this is our graph of our derivative below, when we look at the derivative, wherever the derivative is equal to 0, that's going to correspond with either a minimum or a maximum. If we take a look right here at this one that's just a little past -15, that's going to line up with our relative max. This one that comes across at what looks like -5 lines up with this relative min. And if you continue on through, you should notice that pattern there. Now, critical numbers are x values in which the f of x exists. So in this case, all of these exist. It's not like undefined, or it's not a asymptote or anything like that. And it's where the f prime, or derivative, is equal to 0 or is undefined. So if we did have an undefined portion in here, it would also become a critical number. Now, these critical numbers are important when we're looking to try and find our extreme values. And that's where our high point or low point in the function is. When we're looking for these global extrema, the maximums or minimums, we have a candidate test. And the candidate test basically identifies which numbers potentially or have the potential to become that absolute maximum or the absolute minimum or the extrema. And these include all of the critical numbers, okay, which are, again, the ones that when we take the derivative, the derivative is equal to 0 or undefined. And it's all the y values, it's all the endpoints as well, the y values of the endpoints. Okay, and then we look at those y values all together, and we identify which ones are the greatest number and which one's the least, and that's going to give us our absolute max and our absolute min. Now, let's take a real quick look at once again at another graph. Okay, we've been given this graph here, this f of x, and it's kind of wild and squirrely and everything. Let's answer some of these questions as we determine what is and what isn't our maximums and mins. So the first thing is being asked is, what is the absolute maximum of f? Now, this is our y value, and when we look through here, we can say that right here at y equals 4, our maximum value is our maximum value of f. The next question is, at what x value does f have an absolute maximum? Well, the x value is found right here, and so our x is equal to -4. And so what's the absolute maximum point on f? In this case, it's looking for an x and a y. And so the point is going to be our x is -4, whoops, x is -4, and our y is 4. That's our point. The key thing here is it's asking for a point. I'm going to clean that up again a little bit here, -4. Next thing is, what is the absolute minimum of f? In this case, we're looking for the smallest number of y. And if we notice, it's coming right down over here. Now, if you notice, there's an open circle. This open circle means that it does not include that point. Now, if you encounter this at whether it be a minimum point or maximum point like this, where you've got a close end on an endpoint, or if it's in the middle and it just happens to be on the end of one of the troughs or peaks or the max or mins, the local max or mins. In this case, it does not include it. It is not, there is no minimum point. And the reason for this is when we're going down here, this is approaching -2, but it's not including it, which means, is the minimum point -1.9? Is it -1.99? Is it -1.9999? And you can see this could go on forever. So there is no way for us to determine what the actual minimum is. So we just say that there is no absolute min. Okay, the next question here is asking, what x values does f have a relative minimum? Okay, now we're looking for the next number that's a specific trough or a specific minimum part. Now, if you take a look, we've got one right here at what looks like x is -3. That's where our graph is coming down. We have another one where we have the sharp turn at x equals 1. And we have another one here in which the point has been defined as 1, even though we've got this, the graph continues on up and the limit itself actually approaches 2. The definition of the point puts it at the same level as the rest, which means that it is also going to be a relative minimum point. So we actually have 3 relative mins. We have one at x equals 3, we have one at x equals 1, and we have another one at x equals 2. And so all of them have the same value, which ends up being the lowest value, or the lowest value in that area. Sorry, a relative min. I need to make sure I clarify that. If we take a look at our x values for a relative maximum, okay, we're looking for the peaks here, the high points, okay. You notice we've got 2 high points here. This one here at -1 has got, it includes that point. The one at +2, you notice it's an open circle. Now that open circle means it does not include that. In fact, the +2 has already been included as a relative min because it drops down at that point. So we only have, in fact, one relative maximum, and that is -1 in this case. So this was really an exercise in helping you see or understand that if a point is included or not included, how it affects relative mins and maxes. We have our sharp turn here, that's a minimum. We have this drop down here, that's a minimum. If that point had gone up instead, then it would have been a relative maximum. All right, let's take a look at a situation in which we're given a function instead of a graph, and we're going to see how this works. In this case, we've been given the function f of x equals 1/3 x cubed minus 2x squared, and the interval is from -1 to 3. So the first thing we need to do is identify our critical numbers, and we do that by finding the derivative. So our f prime of x is going to be equal to 3 times 1/3, so is 1, so x squared, minus this becomes 2 times 2, or 4x. We can factor this out, so we have our x is equal to x minus 4. And to find these critical numbers, we set our derivative equal to 0. So in this case, we take one part at a time. In one our x is equal to 0. In this other factor, this would be positive 4. Okay, so that gives us our two critical numbers. Now, one of the things that some of you may have already identified here is that when we looked at our interval ends at 3. This 4 is outside of our interval, so we can't include that. Not in our interval. All right, so we've got our one critical number, and we've got our two endpoints, and this is these are going to be the numbers or values we're going to plug in order to identify which is our maximum and which is our minimum. So our -1, our f of 0, and our f of 3. When we plug in our -1, -1 cubed stays -1, so this becomes a -1/3, and then this -1 becomes squared, so -2, which is going to be equal to, if we convert all this to thirds, this is going to be a -7/3. Okay, at 0, we plug in 0 to this. This is 0 minus 0, or 0. And at 3 cubed is 27. 1/3 of 27 is 9. And minus 3 squared is going to be 9 times 2 is 18. So 9 minus 18 is going to give us a -9. Now of these three y values, we've got a -7/3, a 0, and a -9. Our maximum f, sorry, that's a maximum, is equal to 0. It's our highest point in that interval. And our minimum is going to be equal to -9. That's our lowest point within that interval. All right, let's take a look at another example. In number 8 here, we're looking for the absolute maximum and minimum values of our f of x equals the absolute value of x minus 2. Our interval is from 0 to 5. It's helpful in these cases to be familiar with the parent function and what it looks like. And for the absolute value, we've got a right shift with a -2 there, which would give us a function that looks something like this. Now, if we took the derivative of this, basically our f of x equals 2. And that's not going to help us a whole lot because 0 cannot equal 2. So that doesn't give us a critical point that way. However, we do have a critical point or critical number at our at 2 because it's a sharp turn. And that sharp turn is going to give us a undefined point at the derivative. Okay, it's not differentiable at that point. So critical number is 2 because it's non-differentiable. At 2. Okay, so we've got one critical number and two endpoints. So let's go ahead and plug these things in. We have our f of 0. Oops, f of 0. We have our f of 2. And we have our f of 5. Let's see where these lead. F of 0 is going to give us a -2 absolute value of 2. F of 2 is going to give us 0, absolute value of 0 is 0. And 5 is going to give us 5 minus 2, or 3. Absolute value is 3. So in this case, we get our maximum f is equal to the largest number, which is 3. And our min f is going to be equal to our smallest number, which is 0.